Okay, let's go ahead and work this, this friction example here. And we have some sort of box that we're trying to push across the ground here. And we're asked, how hard do we have to push to make it move? So that's the first part of the question. And before we address that, let's go ahead and draw a free body diagram. So we always have weight, mg, pulling down, and in turn the ground pushes back up with the normal force. Now we're trying to push it, let's say this way. We'll just call that big F, or FP for F push. And in turn there's some sort of friction that resists this. And we're just going to call it, general friction now. We're not going to call it static or kinetic friction yet. We'll address that in parts A and B of the problem. So that's the setup. Now in the first part, part A of the question, we're asked how hard do we have to push to get it to move? Okay? So basically, to make it move, our push force needs to overcome the force of static friction. So this is static friction right now. So we need to overcome static friction. So therefore, remember static friction has a maximum possible value. And that maximum value, so we need to push at the maximum value of static friction. Once we go over that amount, the box moves. So what's the maximum value of static friction then? Well, it's the coefficient of static friction times the normal force. But in this situation, we're on a flat surface here. So it's quite clear, we don't really have to do much calculation to see that the normal force is exactly equal to mg. Okay? So the normal force equals mg. So this is the coefficient of static friction times mg. Okay? So the force with which we need to push then, the coefficient of static friction, so you need to look this up in your textbook. The coefficient of static friction for wood on wood, so this is a wood box on a wood floor, it's 0.5. Okay? Mass of the box, it's 10 kilograms. G is 9.8. So you multiply those out and you get 49 newtons. Okay? So that's the force with which you need to push to make this box start to move. Okay? Now, in the second part of the question, we're told we have the box moving. How hard do we have to push to make the box now move at constant speed? Okay? So now the box is moving, so we're not dealing with static friction anymore up here. We're now dealing with kinetic friction. Okay? So furthermore, we're told it's being pushed at constant speed. Okay? So if it's constant speed, that means that our x acceleration is 0. Okay? So if that's the case, then our push force has to exactly match kinetic friction, because the sum of all the x forces is mass times x acceleration. The x acceleration is 0, so all our x forces have to add up to 0. So the push force then equals kinetic friction. Okay? So that'll keep this box moving at constant speed across the floor. Kinetic friction is given by the coefficient of kinetic friction times the normal force. But again, the normal force, flat horizontal surface, normal force equals mg. Okay? So now we can go ahead and put numbers in. Coefficient of kinetic friction, again, you have to look this up in your textbook. Coefficient of kinetic friction is 0.2. Mass 10, G 9.8. So you multiply those two together, those three things together, and you get 19.6 newtons. Okay? So this again is a really good demonstration of how the kinetic force of friction is significantly weaker than static friction can be. Static friction can be a pretty resistant force. So basically what you need to do with this box, you need to push with a force of 49 newtons, and that'll get it moving. And if you keep a force of 49 newtons, it's actually going to accelerate the box. But if you're just looking to move it across the floor with as little effort as possible, you need to overcome that 49 newtons. And then if you're just going to get it moving at constant speed, you just need to reduce that force to 19.6 newtons. And again, when we finally do our friction lab, we'll actually see this phenomenon where the force of static friction is greater than the force of kinetic friction.